Hello, my name is Denis Nikolaev, and I'll be talking to you about the fundamental limitations on radiation efficiency for implantable bioelectronics. And specifically, we will see how to apply the insights of this study to design of antennas for these incredible devices. You can find more information about our work on this topic on my Twitter, as well as the references relevant to this talk. Wireless implantable bioelectronics offer remarkable capabilities for medicine and basic science. This technology can improve our understanding of living organisms, monitor health, and provide the treatment of many health conditions. For instance, miniature implants can host in near future electroceuticals, neural interfaces, surgical microbots, and biotelemetry devices can sense and transmit glucose levels, intracorporeal temperature, pH, endoscopic data, and so on. And to do this, typical in-body devices rely on radio frequency links with the outside world, although some alternative approaches have been proposed as well. However, we as the antenna designers face some major challenges here. Specifically, the human body is very complex, dynamic, heterogeneous, lossy, and dispersive medium to operate in. This results in extremely low antenna radiation efficiencies. And from the packaging point of view, since we are interested in devices as small and non-invasive as possible, we deal here with very strong miniaturization constraints and dense integration. To address these challenges, we proceed in a following way. First, we study the radiation of implantable antennas and obtain the limitations on radiation efficiency. And second, we demonstrate how to apply the obtained knowledge to the design of efficient antennas. So we start with the theoretical studies, and I would like to talk first about the fundamental limits for implanted antennas. So compared to the radiation into free space that classical antenna theory assumes, we deal here with the finite and lossy medium. And this implies two things. First, the antenna near field fringe into tissues, and therefore the parameters are strongly coupled with the electromagnetic properties of the neighboring tissue. And two, the resulting radiated wave is shaped by the attenuation, complex scattering and reflection, as well as re-radiation as the interface between tissue and free space. In this study, we are interested in this interaction of the source with the finite lossy medium. Since the theoretical efficiencies will strongly depend on the geometry and electromagnetic properties of this medium, we use a simple spherical shape that can be reproduced in numerical and experimental antenna studies. And we use here muscle equivalent dispersive electromagnetic properties. We use two different methods to independently confirm the findings. The first is based on the spherical wave expansion method using elementary electric and magnetic dipole sources. The second uses two-dimensional axisymmetric approximation solved by finite element method, but it assumes more realistically shaped sources. They are shown here and defined via surface current densities in cylindrical coordinates. Tm is equivalent to an electric source, such as dipole or a patch, and Te is a magnetic one, such as loop antenna. The radiation efficiency estimation is based on the Poynting theorem, and since we solve for the field, we can also easily estimate the frequency-dependent behavior of the specific absorption rate for both sources. First, we computed the bounds on radiation efficiency in a phantom with a diameter of 100 millimeters that represents an implantation depth of around 5 centimeters. The agreement between two modeling approaches is remarkable, despite quite different formulations of the sources. We can distinguish three frequency regions. First one we can call a relay regions, where the source and the phantom are electrically small and result in weak radiation and highly localized absorption, as we will see soon in SAR plots. The second region is the optimal one. We can observe strong dipolar response forming around the phantom. And finally, in so-called optical region, we simply deal with the attenuation of the radiated wave inside of the phantom. One important point to take away from this presentation is that the magnetic antennas can perform better at lower frequencies, but the electric ones can achieve higher efficiencies. At this stage, we also did a first preliminary test to see how these results relate to more or less realistic antennas. We designed in CST this very simple conformal patch for 1.4 GHz using PEC and considering lossless materials of the capsule. And its efficiency was indeed very close to the fundamental bounds for the same configuration of the theoretical model. And it fell right between the limitations of the electric and magnetic sources. Next, we consider the effects of the source size. We use two different metrics for this. One is the length and the other is the circumradius of the antenna, as used by the theoretical model. On this plot, we see the maximum achievable efficiency proportional to the circumradius, and here the effect of the source length over the frequency. We see that electric antennas perform better than when larger, but magnetic antennas are preferable for miniature millimeter-sized implants in general. Note that although for an electric source, the efficiency generally increases with the length, however, magnetic sources have sort of an optimal ratio of its dimensions. Encapsulation affects the efficiency as well. Thicker shell results in lower near-field losses, and therefore the electric source benefits much more from the increased thickness. The same goes for dielectric loading. Even more, it has absolutely no effect on magnetic sources, so we show here the effects of the electric one for different shell thicknesses. The efficiency rises until about it's equal to the surrounding medium, which is muscle in this case, and then starts to flatten out. Implantation depth is a very important parameter to consider. Obviously, the optimal frequency and the achievable efficiency both depends on the depth, and both are inversely proportional and related mostly to the increased role of the attenuation. The same model allows us to predict also SAR, how it will behave over the frequency, and clearly the dissipation is the lowest at the optimal frequency range. Note also that at the suboptimal frequency, the dissipation is significantly higher for electric sources, which means it is better to avoid this scenario. However, considering very low input power of modern implants, SAR is generally not a problem here. However, it may be important to remember this for potentially more powerful wirelessly recharged devices in future. We proceed now to the design of realistic proof-of-concept antennas. The design is based on a half-wave patch miniaturized using a high impedance section and ceramic shell with a permittivity of 80, which is close to water at these frequencies. Radiating edges are placed at the opposite ends of the capsule, and this maximizes the antenna aperture. Besides, another advantage of patch designs is that we have a solid ground plane shielding the antenna and from the inner capsule components. And here is the E-field plot confirming that the antennas operate indeed as a half-wave patch after miniaturization. The prototype of one of these antennas is shown below. It is printed on a flexible Rogers substrate, soldered to a short semi-rigid coax cable, rolled and then inserted into the shell that is sealed afterwards. Now a few words about our approach to radiation measurements. On a finalized prototype, we surround the feed with a plastic tube filled with air to isolate it from the phantom by high dielectric contrast. In this way, we reduce the cable effects on measurements. And as the second measure to avoid this, the feed outside of the phantom is fully replaced by an optical fiber that connects to a miniature converter located at the SMA port of the phantom. The phantom itself is a 100mm spherical jar that can be filled with tissue simulating liquids. And for the ease of use, we fix the phantom inside of the electromagnetically transparent Roha-cell foam. So now to the results, and the impedance performance is very good. Moreover, thanks to the intrinsic robustness of miniaturized patches, along with its high permittivity ceramic shell, we can also operate at below -10 dB level in all water-based tissues. The radiation performance is remarkable and close to the fundamental limitations, and these antennas were specifically designed for maximum efficiency. And in collaboration with Ghent University, we have been using these designs for the various measurements inside of large animals as cows, for instance, which was previously impossible with devices of this size. And also at this stage, it's also worth to mention that despite high efficiency, these are very simple antennas. But these design principles can be used to increase the efficiency of more interesting designs. For instance, in recent years, various research groups proposed amazing design approaches and solutions. One great example to mention is a reconfigurable and multi-band implantable antenna designs co-authored by the previous speaker, Professor Yong-xin. And another example is a body conformal metasurfaces that reduce the reflection losses at the tissue-air interface. And this was developed in the group of the next speaker, Professor John Ho. And as a final example, here's a recent contribution from our group. This is not a high-gain design, but this is a highly robust in-body antenna that can operate in any tissue as well as in air. The antenna is integrated on the same PCB with electronics, batteries, and sensors. And here is a photo of a mock-up and a final device industrialized by the Bodycap company. We're sort of proud of this device since it was used on the board of the International Space Station. And by showing here a short summary, I would like to conclude this presentation. So that was a very broad overview, but I hope it gave you some idea about how we can apply the theory to the design of implantable antennas. I'm looking forward to the Q&A session, and also do not hesitate to write me for any follow-up. Thank you very much for listening.